Newton's second law and third law are seen directly through Newton's second law and third law are directly seen in the making and flying of an airplane. So if we look at an actual commercial airplane, this is called an airfoil, which is how the airplane's wing is actually shaped. Newton's third law is seen as equal and opposite reaction. So as the air is exerting the force on the lower wing, the force is exerting, the airfoil is exerting that same and equal opposite force on the air, causing flight. Now, when this force, as we can define the pressure, on the lower wing is greater than the force defined by pressure on the upper wing, and then we can actually find exactly how much lift is being exerted in terms of force for flight. Now, minus drag, when we're talking about horizontal acceleration, which is a different game. So, this is the pressure formula that we've developed, and I'm just basically taking terms and switching them around. But this is the pressure formula that we'll use. It says pressure equals density of the air times the integration of u. Now, what is u? U is the velocity through the gradient of a function which we'll be mapping out, or of the airfoil, we'll just say in simple terms. And u is, like I just said, the direction of flow. So u is actually the velocity through the gradient, like I said. And the gradient is represented by the gradient of the surface areas that we're measuring, which represents the direction of flow. Now, what does this kind of look like? We can see this kind of looks like the second law, which says force equals mass times acceleration. So the way we got this formula using Newton's second law was by saying, okay, force, pressure and force go hand in hand. And then we said mass. Okay, well, what's the air equivalent of mass? Air's density. Then we said, okay, acceleration. Well, that's a tricky one. Well, when we look into the calculus, given our understanding of calculus, not to go too deep into it, a question will. But basically, this, or u, like we said, represents the velocity, so the integration is going to represent the position. So we're taking the acceleration, we're mapping it out into position, so we can get the exact pressure on a certain position plotted on here. Summation of those pressures will be the actual pressure, the total pressure exerted on. So that's how we got this equation, so Newton's second law, and how an airplane relatively flies. Obviously, there's a much more deep explanation to it, but trick-or-treaters. But this will be the demonstration. So we can see the same thing happening follows the same effect of the air is coming in, the pressure being exerted on the bottom is greater than the pressure exerted on top, thus flight. Obviously not the best model of an airplane, but using programs and using analysis that I'm trying to develop, we can actually get the perfect airplanes model, independent of the goals of it. So this is literally for a project for school. I'm gonna include that in the bloopers. So the question I'll be leaving with would be, what effect is being seen that really causes, and that's really the basis for all fluid dynamics and aerodynamics? The answer is going to be the Koppel effect. The Koppel effect is caused by the molecules of matter, rather that be air or fluid, having, this is going to be a zoom of a molecule, let's just say, having high pressure on the top and relatively lower pressure on the bottom of the air molecule, which causes it to stick to its object that it's flying across, because the pressure on top is higher. So it's the Koppel effect. Next question I'll leave you guys with is going to be, how are we actually finding the direction of flow, right? Which was the first question. And we covered the effect, but what is the mathematics behind it? So like I said, it is caused by the gradient. We can find it using the gradient, which is, so the gradient of a function 3 dimensions, represented by x by z, equals a matrix, matrix 1, it equals the partial derivatives in respect to each variable. Now the partial derivatives map out, like when they're using simple derivation, they map out the rate of change in respect to a variable. Now by mapping out the rate of change in each respective variable, the gradient will actually give us